So that way we can, or towards the end of this last time, since we just briefly covered the first step or so of beta oxidation. Okay, and the whole purpose of this is you're going to be breaking down your fatty acids, and you want to completely oxidize them to get all the possible energy from them as you can. And so the ultimate product for this will be acetyl-CoA, and the acetyl-CoA will go from beta oxidation to what pathway? Pardon? Citric acid cycle. Remember, it hooks up with pyruvate. What enzyme is it that will react with the pyruvate with with the acetic acid in order to make citrate? I mean, not pyruvate. Yeah, well, what enzyme is it that will hook OAA up with the acetic acid to make citrate? Citrate synthase. Yes. Okay. All right. Let's see if I can. So once again, the pathway degrades fatty acids to acetyl-CoA, and we've already talked about the fact that this will go on into the citric acid cycle, and also it was called beta oxidation because it's the beta carbon to the ground zero carboxyl group that will be oxidized. Right. Okay, so this is where I wanted to pick up, and I wanted to stress, because it seems like people misuse the term a lot, but in general, we're calling these acyl-CoAs because acetyl-CoA literally means that there's only two carbons, but acyl means it's the acyl to carbonyl group followed by, several, X number of carbons, okay? And so that's why a lot of these enzymes will have generic sounding names. This does require FAD to make FADH2, okay? And this was the one exception in the sense that I told you that there's one naturally occurring trans fat, and so it's going to be this trans-enoyl CoA. And it doesn't leave. You don't have to worry about these trans fats leaving and clogging your arteries because, unless you have something majorly wrong with you, because the fact that stays within the beta oxidation pathway. All right, so what class or classes of enzymes could do this? Knowing what we know so far. Dehydrogenase, and if you're going to name this one, what would you name it generically? Acyl-CoA dehydrogenase, right? And I forgot exactly if we stopped after this point, if we made it to one more, but this is the one trans fat, once again, that we are in the process now of oxidizing the beta carbon. So the step 2 is a hydration reaction, and it's going to hydrate that enoyl in order to make it a hydroxyacyl-CoA. Okay? So now this one is clearly it's easy to see, I should say, how, let me see. Oops, there, it's a little off. The beta carbon, because once again, there's ground zero, so there's alpha, beta. And the beta carbon now is becoming oxidized. And so what class or classes of enzymes can do this type of reaction of going and adding on an alcohol group from a water? Maybe a hydrolase. What's another name for hydrolases? Sounds a lot like it. Because what's this process doing? Like if you're adding water to something, like you're trying to add moisture to your skin, what do you call it whenever you're thirsty and you're trying to rehydrate? Okay, so what class of enzymes could this be? I feel like I'm doing charades. Hydratase. Okay, and so this is a hydratase, and so if you're going to name this hydratase, what would you call it? Say it with some conviction. There you go. Technically it says enoyl-CoA hydratase, but I would accept trans-enoyl, just being a little bit more specific. Okay. So remember that video that I showed you that was called the force based off of the Ting Ting song? So we have already oxidized. Now we hydrogenated it. And so we come to the third step, which is another oxidation group. And we're going to go now from the hydroxy to a keto, once again at the beta carbon. And so This also requires an NAD, becoming NADH. Remember, we're going to find out that every FADH2 that's made ultimately go on to form 1.5 ATPs, molar equivalents. Every NADH that's made, for the most part, will go on and form 2.5 molar equivalents of ATP. So what class or classes of enzymes can do this? Dehydrogenase, and if you're going to name it, what would you name it specifically? Say it with some conviction. Come on, not wishy-washy. There you go. Beta-hydroxyacyl-CoA dehydrogenase. Okay. And the fourth step is a cleavage reaction, because we've got to cut off what will become acetyl-CoA. Okay? That was like, I said that with more conviction than you did in guessing the enzyme name. So there was oxidation, then hydration, oxidation once again, then cleavage to form the acetyl-CoA product, and to get another, to be ready to go to the next step. Okay? Unless, of course, if you're down to 4 carbons and you get 2 acetyl-CoAs as your product. So this requires coenzyme A. I will tell you right now, it's the only one of the 4 that has its special name. And we're going to see it in the future. You know, people always forget that, and I always tell them, you're going to see this in the future again. You'll probably forget it. But this enzyme is important. It's in multiple pathways. This is actually named after the kind of compound it is. Sort of like we had aldolase and enolase. We've now got this one. So what are some of the functional groups that are important here? What will be the nucleophile?
The sulfur.
The sulfur. And what is that functional group called?
Thiol.
Pardon?
Thiol.
Thiol. Okay. And so this would become thiolase. Yep. Because it is the reactive thiol of the acetyl-CoA that will come and smack the beta carbon. You get a tetraketyl intermediate, and then you get collapse, essentially, to ultimately get your acetyl-CoA and then the next acyl-CoA. Unless, of course, we're down to 4 carbons. If you're down to 4 carbons, then 2 products would both be acetyl-CoA. So this just shows you an example. And remember, I already told you how to determine the total number of cycles it would require. You take the total number of carbons for an even chain fatty acid. You divide that by 2, and you subtract 1. And that's because that last time, when you have 4 carbons, you're going to get 2 acetyl-CoAs out of it. So that's why if you had sterile CoA, which is octadecanoyl, if you're going to go according to IUPAC names, since there are 18 divided by 2 is 9, 9 minus 1 is 8. So it's going to require 8 cycles of beta oxidation. But ultimately, you get 9 acetyl-CoAs, 8 NADHs, 8 FADH2. So you can see how much more energy you get, since each of these, each of these will go on to make 2.5 ATPs, and each of these will go on to make 1.5 ATPs. And then the acetyl-CoAs also go into the citric acid cycle to get more FADHs and GTPs to ATPs and things like that. And so it's very, very much more energy efficient in that sense than this glycolysis alone. This is the picture. It's a spiral. And so we had, glycolysis and gluconeogenesis, which essentially were linear metabolic pathways. And we had the pentose phosphate, which is kind of crisscrossy. And citric acid cycle, of course, was a circle. And now beta oxidation is a spiral. And the reason why is because every round you lose 2 carbons, so it's 2 carbons smaller, until that last round, whenever you have 4 carbons and you get 2 acetyl-CoAs. Are there any questions over the 4 enzymes before we start talking about other things. If you don't like that little spiral, you can also look at that, because that's from the older book. This is just another picture from the current book. To me, it looks more like a slinky. Slinky, magical toy. Alright, so obviously you guys are way too young to know the little Slinky song from the commercial. But I mean, it's not what it's from, but it's an actual commercial from the 70s and 80s. That's really sad. Okay. Alright. So where do the products go? Why is this important? We've actually been answering this. The acetyl-CoA goes directly into the citric acid cycle. The NADH, FADH2, where do they go? What metabolic pathway does NADH and FADH2 go to? The electron transport chain. Okay, and that's the reason why. And where did beta oxidation occur at once again? Because I didn't cover that. The Holy of Holies, which was the mitochondrial matrix, okay? And so that's why we don't have to worry about it being a cytosol and trying to ship in the NADH or the FADH2. Because remember, neither one of those can actually go directly into through the mitochondrial membrane, so they have to use a malate dehydrogenase shuttle. But we don't have to worry about that because it's already in the Holy of Holies, where the beta oxidation occurs. Okay, now what about the special fats? Okay, before we were only talking about saturated, but we have unsaturated fats. So we have both cis, which are naturally occurring, and we've got trans. We've also got what happens if it's an odd numbered. There are some that are odd numbered fats. Okay. Most of them are even numbered, but there are some. We're going to find out that that's important actually for some of the odd numbered ones. You just don't hear about them very often. Okay, so for the unsaturated fatty acids, what's an unsaturated fat? What PUFA means is polyunsaturated, but it just means it has a double bond, and these, like I said, they're naturally occurring, then they are going to be cis double bonds. And these are the ones that we always talked about, being the healthy fats. Okay, so this is oleoyl-CoA, or oleate. And it has a double bond between carbons 9 and 10, and that numeration is going from the alpha end. Remember whenever we talk about omega-3 or omega-3,6 or something like that, that's when the numbering is coming from the back end. So what happens is normally you just go through normal beta oxidation until you get within 2 carbons from the double bond, okay? And what happens is it gets stuck because that double bond is not a trans fat. It's a cis fat. So we have to have some type of enzyme that will convert it to the trans stereoisomer. Because the enoyl CoA hydratase is the one that recognizes it as being a trans fat. Let me put this with my joke. Which I thought I was going to be running late once again, as I stopped at Starbucks. And a well-meaning, well-intentioned young man decided that he should lay hands on me and pray for me. And so, once again, I was like, well, thank you. I've got to go on to work now. So, all right. Yeah, just some of the people that you can just meet. So this is the example I was going. So the oleoyl-CoA in the specific example would undergo 3 types of normal cycles of beta oxidation until it gets to the cis bond starts 2 carbons away. And so this is, and if you remember from organic chemistry, the numbering for the double bonds, it's always a lower number that gets set. So that's why when we say it's and 2, it's on carbon number 2, it's really going to be between carbons 2 and 3, not between carbons 1 and 2. And I wanted to point that out because, as you can see, it moves. Okay, and so right now we get to the cis that's on second carbon, or the beta carbon, away from the ground 0. And we have this enzyme that will convert it from being a cis 2, or at the beta carbon, to a trans at the alpha carbon. Okay? And so if you think back to last semester, and we talked about how in biochemistry we use the delta sign to indicate double bonds. And so that means delta 3 because that's the beta carbon. This is technically carbon 1, carbon 2, carbon 3. So that's why it's a cis, delta 3, whatever, acyl-CoA. That dodecanoyl just means that it's got 12 carbons left in it. And you're going to make a trans delta 2 acyl-enoyl-CoA. So what class or classes of enzymes could this possibly be? This is an isomerase, because cis and trans are isomers of each other. So if you were going to name this, what would you name it? Well, the dodecanoyl is a specific number. That means 12. But this is just, so what's a generic instead of saying dodeci? Pardon?
Trans fatty acid.
Nope, we still have to say what functional group is there. We just don't say the dodes part, the dodes. This is an enoyl. Enoyl-CoA, don't forget the CoA because it has to have a CoA. Enoyl-CoA isomerase. And not only that, but it's even more specific because it tells you it's the delta 3, delta 2. It's going to isomerize between those two carbons. So that's why that enzyme tells you explicitly what it does. It's going to isomerize between carbons 2 and carbons 3, the enoyl-CoA. So it's going to convert it from a delta 3 cis to a delta 2 trans. And then you're fine and dandy just to go ahead. The enoyl-CoA hydratase can then do its job, followed by the dehydrogenase, followed by the thiolase.
So we gotta draw those two deltas in there.
Yeah, I mean, technically that is its name, delta 3, delta 2. Okay.
So this only happens for cis unsaturated.
Right. Right. Because for a trans fat, technically, as long as it falls in the correct spot, which would be at the delta 2 position, the enoyl-CoA hydratase can use it as a regular substrate. Okay. So it's not the fact that trans fats are bad for you because our enzymes can't break it down. They're bad for you because they have such high melting points, and so they clog your arteries. They clog, it doesn't even just have to be your arteries, they clog lots of places. Okay, so what about the PUFAs, the polyunsaturated fatty acids? This can be a problem for two reasons. One is configuration. You have to worry about cis versus trans. And the second thing has to be the location of the double bond. In order for beta oxidation to work, you have to think about where the double bond has to be with respect to the enoyl-CoA. And so if we go back, let me just try to explain what that is by showing it. What I mean by that is the double bond, even if it's a trans, it has to be starting at carbon number 2. Whereas up here, this was cis, but it's also starting at carbon number 3. Okay? So there are two auxiliary enzymes. This is just linoleic. I'm not even going to try to undo years of speech therapy by trying to say its IUPAC name. Well, I can't do it. But linoleic acid, which is a delta 9, 12 PUFA. And this is just a specific example, by the way. Okay. So once again, you're going to undergo beta oxidation, clear up until you get to where the double bond is at position number 3. Okay. Now, for this specific example, when it's at position number 3, boy, this is really tiny, so I'm trying to see it. When we get to this point, is the problem here the configuration, meaning cis versus trans, or is it the location? Is it not at the right spot for any of the enzymes to get it? And so it's the configuration because it's cis. Okay, so what enzyme can we have, or do we have that can make it go from cis to trans? The one that we just talked about. Okay, so it's configuration. It's the delta 3, delta 2 enoyl-CoA isomerase. Right now, it can undergo one step. Because if you remember back to last semester, many of these are these naturally occurring PUFAs. The double bonds occur every 3, like 9, 12, 15, 18. Okay? And so that's why this next step is important. So you can undergo one round for that first cycle, and then what happens is now we get here, where we have the trans at the delta 2 position, and then we've got a cis at delta 4. So now is the problem here the configuration, or is it the location? This one's a location issue, okay? And so we're going to now use, let me check, see. Yeah, we are now going to use a different enzyme than the isomerase. This one utilizes NADPH, okay? And so what class or classes of enzymes can do this? Okay, dehydrogenases. Oops, want to make sure I didn't blinding by, I keep accidentally hitting the laser pointer. Okay, the dehydrogenases. What else? Some of these also had multiple names. That was one class that uses NAD, NADH, NADP, NADPH, things like that. Reductase, or oxidoreductase. But yes, so what would you name this one? It is a reductase, by the way. So this is 2,4-di-enoyl-CoA reductase. Whereas if I gave you that name of that enzyme, you could probably tell me, oh, that's going to reduce 2,4-di-enoyl-CoA. That one, for me, that was always the one that I had problems with, because it's just, first of all, they use the older term reductase, but secondly, the 2,4-di-enoyl part. Right. So now what's going to happen at this last step? Okay. What can we do here? It's the isomerase. Yep, whoops. It does not go. There we go. So it's the enoyl-CoA isomerase once again. All right, so we're going to see that we've seen that enoyl-CoA isomerase doing a lot of work here, but then we do have this new reductase for the PUFAs. And once again, these are those that are naturally occurring where the cis double bond is every 3rd carbon. And so if you have like arachidonic, which has what, 4 of them, then you're going to have to use it 4 times. Well, technically you'd have to use it, I guess, 3 times. Okay. All right. As I mentioned before, the vast majority of naturally occurring lipids have even numbers. We've seen them 12, 14, 16, 18, and 20. Those are the common ones. However, there are a few that have odd-numbered fatty acids. Plants can do this, certain marine organisms, and ruminants. And ruminants form propionate, which propionate from organic chemistry comes from propionic acid. That just means it's lost its hydrogen. So what do you suppose it looks like? What will propionate? Right, it's a carboxylic acid that's going to have 3 carbons in it. All right, and so, and ruminants, what are ruminants? Well, sometimes people, especially pre-med, may not know what we'll talk about with one ruminant.
Cows?
Cows.
Is it any like mammal that like digests something several times?
Right, where they, yeah. So cows, sheep. Okay. And then also, it's used in a lot of bread as a mold inhibitor. And so we do get propionate in our diets in various ways. So we have to have a way in order to digest these fatty acids. So you get normal beta, go through normal beta oxidation until you have the last 3 carbons. Or if you're starting off from propionyl-CoA, then it's going to be just the last part, okay? And it requires 3 additional reactions. All right. So we get to see some players once again, and some new players like coenzyme B12, which is awesome. Okay, so if you think back, what does biotin do? What kind of reactions is biotin often used in? The transferring of like acyl or carboxyl groups, okay? And so this uses up an ATP, and it adds the carboxyl group to make methylmalonyl-CoA. What class or classes of enzymes, I can think of at least 2 off the top of my head, maybe 3, that can do this kind of reaction? What's one of them? Maybe a synthetase. That's definitely one of the big 2. What's the other one?
What did you say? So I was going to say kinase.
Well, this wouldn't be a kinase because we're not adding a phosphate. Maybe a transferase. Then there's a third. That was the one that's the maybe one. Synthetase made the most sense, but it's not synthetase. It's not transferase. What else is technically being transferred here? Carboxylase. This is a carboxylase. And so if you're going to name this one, what would you name the specific one?
Propionyl-CoA carboxylase.
There you go. Propionyl-CoA carboxylase. All right. So for the next one, there are 2 possible answers that I can think of here. Off the top of my head, the right one and then the one that most people will guess. What is actually happening here in this step? It may help if you know that methylmalonyl is a type of sugar. Or is a carbohydrate, if you want to think of it that way.
The acyl and the CoA are switching.
Right, they're switching. So what are some of the kinds of enzymes that can do these switching? Maybe mutase or isomerase? And what's the third? It's specifically with isomers of sugars in particular. We've only seen it, I think, once. Epimerase. And this is an epimerase, okay? And so its specific name would be, oh boy, somehow it has decided to go to sleep. There we go. Methylmalonyl-CoA epimerase. Okay. Now, coenzyme B is doing something very special here that we haven't seen it do specifically. All right? So where does coenzyme, I'm about to give it away, where does coenzyme B come from?
Sorry, what was that question?
Where does coenzyme B come from? Okay. Right, but, I mean, what precursor is it? It's a vitamin.
Good for your brain.
It is good for your brain. You know how Jeopardy has, sometimes it's been a long time since I've watched, but they had like those stupid answers. Was one of the categories. It comes from vitamin B12. So coenzyme B12 comes from vitamin B12. And it's called cobalamin if you wanted to know the official name for it. But yeah, it's vitamin B12. And this, by the way, is methylmalonyl-CoA mutase. Why they went with the mutase versus the epimerase or isomerase, I don't know. But it is. And this is one of our few times that we get to talk about a new reaction and how vitamin B12 works. Okay? Or if they talk about something being cobalamin dependent, I mean, that's just the the biochemical word for, coenzyme B12. First of all, if it's cobalamin, what do you suppose, what metal is important for cobalamin?
Cobalt.
Cobalt. And we don't get to see cobalt a lot. So vitamin B12 transfers alkyl groups, or even substitute alkyl groups. But it has to have a hydrogen next door to it. Remember, vicinal means neighboring. The neighboring carbon has to have a hydrogen. But what makes this different than anything else that we've seen? In the past, we've seen things remove hydrogens and stuff because the hydrogen can get exchanged by the NADH, by the water, or something like that. It's protonated, or not protonated, it becomes a proton and so it gets plucked off. But what's remarkable about this is it does not leave. It actually cannot be plucked off by the water, okay? So how can the hydrogen move without mixing with all the different hydrogens that's present in water? And if you think about this, that was one of the issues with alcohols with NMR, remember, and with amines, by the way, where the hydrogen is constantly popping on and off with the water, all the water molecules. You can't really tell. It's called solvent exchange. It does not happen in this reaction. And so instead, this is vitamin B12. It's huge, okay, but it contains a trace amount of cobalt. And it's got a ring called the corin ring, which is similar to the porphyrin ring of heme, except for heme has what metal in the middle? Iron. Okay. And so what happens here is you get this complex because it requires an ATP, and it's only one of two reactions where this occurs, and it's where the phosphates are the leaving group. It's like the entire triphosphate is a leaving group. The other reaction is going to be from SAM, which stands for S-adenosylmethionine. And so that's really important. This only happens two times. Where normally when we hydrolyze ATP, we get either AMP or ADP as the product. Here, you just get DA added and you get a triphosphate as the other product. Okay, you have to be careful otherwise it sounds kind of bad if you talk really fast and you say that. All right. So this is how the reaction works. Oh, first of all, I forgot, I was looking ahead. Reaction occurs between this DA, the deoxyadenosine, and the cobalt. And so if you notice, cobalt is a 3+ charge here, and it actually produces a radical. So it's a type of a free radical that's going to be occurring. And the hydrogen never exists by itself. And I'll show you what that looks like in just a moment, because it's hard to draw for sure. This is what happens. So cobalamin attacks ATP, kicks off the triphosphate, which the triphosphate can then be broken down to get even more energy from it. And that's when you get your coenzyme B. So it's a cobalamin group with the chlorine ring. It has the attached DA on it. And then you get this cycle. And so whenever we do free radicals, they don't do the electron pushing quite the same. But what happens here is that you have the linking carbon between the cobalt and the DA. And then what happens is this is a relatively weak bond, and one electron goes with the carbon and one electron stays with the cobalt. So if you now notice, cobalt has been reduced to 2+. 3+ is the oxidation state that's required for the vitamin B12 to work. All right, then you have your substrate coming in. And what happens is when the substrate comes in, the free radical here hooks up with a hydrogen and one of the electrons. And so now you've got this methylated DA and the substrate radical, but the substrate radical doesn't leave. It doesn't leave the enzyme, so you don't have to worry about it going and attacking a lot of things in the area, assuming that you have a healthy enzyme, a healthy cell. Then we get a radical rearrangement, and so what happens is the halogen jumps, so you get this halogen shift, where the radical now is one carbon over. That's the reason why you have to have, I said halogen, I'm sorry, where the whatever group it is, the alkyl group that is being moved is shift over. Okay? So that's why you had to have a hydrogen on the vicinal carbon. And then you just get the reversal. The hydrogen with one electron goes and hooks up with what will be the product, and the methyl group is the radical there in your vitamin B12, and then the cobalt will give one electron back in order to form the bond, and so that's why you rejuvenate your cobalamin B12 coenzyme. So for this to work, whatever group that you're moving over has to be adjacent to a carbon with a hydrogen on it. Okay. And then finally, plants and animals do not synthesize this vitamin. Okay, we have to obtain it in minute amounts. There are only like 3 micrograms per day, and there's only a handful of species that synthesize it, microorganisms. Okay, and so there are many instances where people either fail to get this vitamin from intestinal bacteria or from ingesting meat, and you get what's called pernicious anemia. There are other diseases, by the way, that's also a factor where your body just doesn't adjust to the symbiotic relationship with the bacteria. This is one times when it's good to have the gut bacteria, but it only gets bad if that bacteria that's normally in your gut gets moved to another part of your body. Okay. But what happens is in pernicious anemia, you don't get enough intrinsic factor. Okay. So that's required for vitamin B absorption. So you have a reduced number of erythrocytes and reduced hemoglobin, hence the anemia. And you can get severe progressive impairment of the central nervous system with it. There are other disorders that are digestive disorders that are either due to a decreased amount, you didn't get enough vitamin B12, or that you're having problems getting it from the bacteria that is available in your gut or from your diet. Okay, and so for people who are, especially people who are vegan, then or vegetarian, then what they do now is a lot of times they supplement a lot of the soy-based products with some of your B vitamins to help make sure that they can get enough of it in their daily diets as well.
That's because they super clean the produce network. Because it used to be, I guess back in the day, everything wasn't so clean, so it was
Right.
dirt.
Right, yeah. So now everything, that's one of the reasons why, there's that whole theory, one of the reasons why it seems like people are more allergic nowadays than before is the fact that we've become so clean as children. We protect our kids too well.
I saw something about that with the dishwasher. It was like dishwashers have aided in more allergies.
From being so clean.
Yeah.
Yeah, another one, I saw a study, it's been some time ago, where also if with infants and small children around dogs and have dogs and they have healthier immune systems or less allergic than ones who are around cats or have no pets at all. They think it's not so much the animal itself as the fact that the dog is really friendly, and so the kids get in their face and you get all over, and so you just
And the dogs go outside.
right. The dogs go outside and everything, but yeah, whereas a cat, either they're not going outside or if they are outside, they don't. This is usually or as a social animal as a dog. And so, yep. Are there any questions?
Well,
over?
what happened if you had like a vitamin B12 like over consumption?
Offhand, I'm not for sure. I don't know that how much it would require. I mean, essentially, too much of anything is bad, right? You can have vitamin C toxicity, and so I'm sure that there's a vitamin B12 toxicity level. I just don't know how much you'd have to partake of in
Yeah.
order to reach it.
Because like the 5-hour energy boosters has like a higher dose. Than
Oh, they
B12.
do, yeah. Or even people who take multivitamins, you know, they usually have more than 100% of the daily, and so the daily minimum that's needed. So at this point, I've never heard of anyone having vitamin B12 toxic shock or anything like that.
Yeah. I was wondering